Just to finish what we're talking about, okay, we talked about you have water moving through, so there's still soil moisture in these particles, but mostly there are air spaces between the particles until you reach an impermeable layer down here at the bottom somewhere and it starts to back up. At the water table, you start noticing that all the spaces are full of water, so we say it's a saturated zone, whereas above that is unsaturated, it's not full of water. Okay, normally we would see this groundwater going underground, and generally the water ground table also moves downhill, just for the record. Okay, sloping down to here. Okay, if the surface touches the water table, so for example on this one the normal water table is right here. If it breaks the surface, then this water may leak out into the surface, which basically is what a spring would be. Okay, and this feeds the stream. If you have year-round streams or streams that are mostly year-round, they probably are fed by streams and underwater, the groundwater underneath here that's leaking into at the surface. All right. However, if you get a drought, notice this dotted line down here. Okay, then it's below the surface, and this stream would eventually dry up at that point. Okay, and some streams are like that. We call them intermittent streams because they don't always have water in them. Okay, now if we were to drill a well, if we drill it down to the water table, then we can get water from the well. But once again, notice if we don't drill deep enough during a drought, the water table may be lower than our well, and we would either have to re-drill the well deeper or drill a new well because we're not reaching it. All right, and so always want to make sure we drill a well deep enough to actually get down into the water table and below where it might go in a drought. Now, talking about some of the cracks where springs come out at the surface or so forth, a lot of times these are called by faulting and things that we talked about earlier. Just I'll throw that in there. Okay, now if rainfall can fall in and fill into the top of this is called an unconfined aquifer or the unconfined water table. Okay, and it basically fills up straight across. Okay, water can come in, fill it back up. So this is what we call an unconfined aquifer because it has a bottom layer that's impermeable, and that causes water to pile up above it, forming the water table. But there's nothing stopping the water from coming down into it. However, underneath that layer, there might be another impermeable layer, and while none of this water can get down to it, where these two rock layers come up to the surface over here, there's an area in between here that drains into that water, that area between the two layers. Okay, now this is considered a confined aquifer. Okay, and since it fills up, it's gradually flowing this direction also, just like this one would probably be flowing down toward the ocean or downhill. All right. But since it can only go here, it starts backing up, and it can put a lot more pressure in this one than there would be in this lower one. All right. Now, if we're to drill a well down here, we break through this layer, and so now the water can come up here. Well, fluid pressure, we talked about this last time, however tall it is over here, water over here can flow to the same amount, same height as the water here. So this water, instead of just flowing to the surface and spreading out, it's under this high much pressure, so it's going to shoot up almost as high as that. And so you might have high pressure water coming out of this. This is called an artesian well. In this case, the well would be considered an artesian well or an artesian aquifer because this confined aquifer builds up more pressure over here, and so when you tap into it, the water will try to flow up to this height over here and actually come shooting up out of the ground, and so that's kind of always fairly impressive looking. Now, notice though, the only place water can get in this confined aquifer is over here in the recharge zone. So that makes this a very important area. If we were to start building factories and parking lots and shopping centers and stuff like that, now if no water can get in here, or we reduce the amount because of all the concrete and asphalt and houses that we put in this area, Now you basically cut off the source of water, and eventually this one's going to get lower and lower and lower as the water flows away downstream, very slowly, but it will keep flowing, and eventually you're not recharging it. For example, in Austin, the west side of town, there's a Edwards Aquifer recharge zone, and there are very strict rules about what can be built there, or if anything can be built there at all, because this is where all the recharge area to the aquifers that they use for their water supply. Okay, and so recharge zones can be very critical to a confined aquifer. Okay. All right, going back talking about our wells again, if you draw a well in an unconfined aquifer, then the water will leak into, there's usually holes in the pipes that allow water to drain into it, and it will fill up to the level of the aquifer around it. Okay, if you go into a confined aquifer, it will rise up to that same length that this will, but if the landscape is deep enough and there's enough elevation there, then it will just rise up higher. So it would come up higher and be easier to pump out of. Okay, but once again, if it's lower than the top of the aquifer, you would actually have the artesian well where it springs out to the top. All right. Now notice the unconfined is easily recharged. The confined, there's only a certain area that can recharge it, and so it's very critical how that area is treated. Now it is also possible to have something called a perched aquifer. In a perched aquifer, you have some type of, this is called aquiclude, I think they call it, but at any rate, you have some kind of impermeable layer here. Okay, and so the water that comes down starts to build up here, and you can see where it builds up. All right, over here where it hits the surface, this impermeable layer hits the edge, then you might have springs leaking out and coming out here. These people here have sunk a well down here, and you can see how they're starting to pump water out of that. However, since this is not the main aquifer, it's a fairly small here, and it's possible, especially if they had neighbors and they started putting wells down here, that you might draw out all this water and run out of wells. So sometimes people hit an aquifer and they think, oh, they're in the main aquifer, but if they're only on this perched water table or perched aquifer, then it may not have a lot of water in it, and it may run dry from time to time. Okay, and it may be worth drilling even farther down here to the main water table. Okay, so I'm put this well in, so oh, it didn't work, so they went here, yeah, we got water, but it may run out in dry times, so you may just have to drill a deeper well and get down here into the main water table. All right, but that's what a perched or elevated aquifer just means. It's up here, there's a, not a solid, but a part of an impermeable layer here that traps water right above it, and a lot of times these can cause problems for people drilling because they think they've got water, but they're not down the main aquifer. All right, and so it may not be a steady, reliable source of water in drought time. Now, we said water moves downhill, whether it be on the surface, it runs off into the stream. Same thing is true in a aquifer. The water is moving downhill toward a lower area. Okay, and the movement of the water depends, one, on how permeable it is. The higher the permeability, sandstone, gravels, sands, these would be very permeable levels. So if you have a high permeability, it will move faster. If you have smaller particles like clays or silts, then it's not going to move very fast through it. Okay, and it also depends on the rise, how high it is over here versus the run, which is how far it goes this way. Okay, obviously if the rise is there but the run is only short distance, then it's going to be steeper and it's going to flow quicker. If it's more flatter out, just basically rise over run is slope, so if it has a slow slope, then that's going to do it a lot less than one that's sloped like that. Okay, it's going to have a faster movement, but at any rate, just keep in mind that the movement is very slow. It may only be a few centimeters per day. Okay, so unlike water surface runoff, which can be very fast and cause flooding and so forth, okay, this underwater movement is very slow because you're moving through, in some cases, rock, like sandstone, could be gravel, could be whatever, but a layer of sand or so forth. But it's going to move very slowly because it doesn't have a free movement through the material. It's actually moving through a rock layer and cracks and stuff like that in it, or actually between gravel particles. So it's going to be very slow, kind of like if we do soil samples, which hopefully we will do today or have done in lab whenever we get there. Once you fill it up, it takes a long time for the water to drip out, once you filled up the soil, it's saturated. It takes a long time for water to move on down. When the soil is dry, it moves in very quickly, but then it takes longer. Now, subsidence can also be a problem with groundwater sometimes, and this would be land subsidence. Make sure I spell that right. Subsidence. The same word we get subside, means to sink. Okay, the Leaning Tower of Pisa is probably one of the famous ones, as they built this tower on top of the ground underneath, subsided or compacted on this one side, and now it leans that direction. They've done things over time. They've kind of built up new layers at different angles and so forth, but basically they're just breaking even. Okay, they're keeping it from getting any worse, but they haven't really been able to fix it. So subsidence then has to do with subsiding, because in this case it could be weight, but it could also have been related to groundwater. If you have a rock layer, just say it has sand in here, if there's water beneath here, when it has weight on it, if you push weight on that water, if it's trapped and can't go anywhere, it feels very solid. Just like if I have a syringe full of water with a cap on it and I push on it, I can't compress that water, and so it feels pretty solid. But if I pump the water out, then these particles will start subsiding and they will kind of flatten out. And since there's no water in those pore spaces, they get more compressed. And so the land above it, the pressure of it will squish it closer and closer together as we take the water out. This can be a big problem. For example, if you're in Houston and you're only, say, 25 to 50 feet above sea level anyhow, as they pump more and more groundwater out, the groundwater starts to sink, and if they're not careful, they're going to be like New Orleans, where they're actually below sea level and they start building levees and dikes or something. All right, now this is an example in California. I won't say San Joaquin, but one of the valleys where they do a lot of farming, and they've been pumping out lots and lots of water. And you can see that in 1925, the land surface would have been up here. 1955, down here. 1977, and I would guess now it's even sunk farther. And they're just saying the elevation of the land has actually sunk because it's getting lower and lower as they have pumped out this water, and those layers get more compacted. So as you can see, that can be a fairly serious amount of subsidence. Had this happened, say, for example, like we're talking about in Houston, but it is happening in Houston, you know, they could be dangerously underwater, but fortunately for them, they're farther inland and have a higher elevation. So, but that land subsidence is where it begins to settle and pack down as you pump the water out, and it can really result in dramatic changes in elevation. All right, now another thing that can happen is carbonate dissolution. Okay, CO3, carbonate dissolution, which basically just means to dissolve. Okay, and what happens is as water comes through water reacts with carbon dioxide, and it mixes H2CO3, which is carbonic acid. Now, it's not a real strong acid, not going to hurt you or anything, but as it goes through rock layers, especially limestone, as you can see here, it dissolves it. And so this is what causes caves. Okay, over time, it's dissolved and dissolved and dissolved all these ways. Also, they make the water, as it dissolves, it leaves carbonate deposits, which makes new formations. But you have these caves form where basically over time has dissolved the limestone, particularly here's around Austin. There's some out in Kentucky, and basically you just get these big empty spaces over there. Okay, and this comes from the groundwater just dissolving that carbon away. Some actually have rivers that flow through them and carry away stuff, so you get that as well. But basically, if the cave's roof collapses, then you have a sinkhole. Okay, and this is known as a karst region or karst topography. K-A-R-S-T. Karst topography is where you have a bunch of these caves and stuff, and like I said, Kentucky, there's some places in Yugoslavia that they were originally named for. There's where the karst idea came from, the name karst, but Kentucky, central Texas around the Austin area, and San Antonio, there's a lot of caves down there, and very often rivers may just disappear, for example, and then they show up again as springs later on and come back and start flowing again. And so you have underwater rivers and lakes and stuff like that. Generally, these are rough, rugged areas that have thin soil, rocky surfaces, high runoff, and so they have a lot of flooding as well as those things. All right, and we will stop right there and pick up again in the next video.